So now we'll go through the solutions to the multiple choice problems on the review. Don't forget to also look at reflections for a more complete review for the test. Number 1, a study of voting shows 663 registered voters at random shortly after an election. Of these, 72% said they had voted in the election. Election records show that only 56% of registered voters voted in the election. Which of the following statements is true? So statistics are from samples, and 72% is from the sample, so 72% is a statistic. So that kind of narrows it down to either A or D, right? Because there it has 72% as the statistic. Now, what's a 56%? That's the true proportion of the population that actually voted, so that's a parameter. So our correct answer is D. 72% is a statistic and 56% is a parameter. The Gallup poll has decided to increase the size of its random sample of voters from about 1,500 people to about 4,000 people right before an election. The poll is designed to estimate the proportion of voters who favor a new law banning smoking in public buildings. The effect of this increase is to, well, when we're dealing with sample size, remember that n is in the square root in the denominator. So the square root of the sample size is in the square root of standard deviations for both proportions and means, and it's in the denominator. So the bigger the sample size, the less the standard deviation, aka the variability. So it will reduce the variability of the estimate. Number 3, suppose we select a simple random sample of size n equals 100 from a large population having proportion p of successes. Let p hat be the proportion of successes in the sample. For which value of p would it be safe to use a normal approximation to for the sampling distribution of p hat? So since we're talking shape, that is the large counts condition for each proportion. So we're going to test it for all 5 scenarios. So for the first one, p is 0.01, right? And 100 times 0.01 is just 1. It is not at least 10, so it's not met on the number of successes. For the number of failures, it is met, but you got to hit both. So just getting the 99 here is not good enough. You need to show me calculations for both. All right, then we try 0.09. Again, not at least 10, so we're going to move on. And then we try 0.85, and we get 85 and 15. Both the expected number of successes and the expected number of failures are at least 10. So we can use a normal approximation for C. We'll go ahead and continue checking on. Whoops, I'll do the last one first. And then here's the other one. Both of these have the correct number of successes, but they do not have the minimum number of failures. You need at least 10. So the correct answer in 3 is C. Number 4, the central limit theorem is important in statistics because it allows us to use a normal distribution to find probabilities involving the sample mean, not the proportion, by the way, the sample mean, so we look at if sample size is reasonably large, if it's normally distributed, and if it's both, if it's the population size is reasonably large, or the population is normally distributed and the population standard deviation is known. Well, here's the definition of the central limit theorem. It states that if you have a population with mean mu and standard deviation sigma and take sufficiently large random samples from the population with replacement, then the distribution of the sample means will be approximately normally distributed. Okay, so the correct answer is sample size is reasonably large for any population. Number 5, a researcher initially plans to take an SRS, or simple random sample of size 160 from a certain population and calculate the sample mean X bar. Later, the researcher decides to increase the sample size so that the standard deviation of the sampling distribution of X bar will be half as big as when using a sample size of 160. What sample size should the researcher use? So we want the denominator to be twice as big for our new n hat. And the old denominator is square root of 160, which is 12.65. I double it, and I get 25.3. And so if I want 25.3 to be my new denominator, that means the square root of my new sample size is 25.3. I can square it, and I get 640. Now, you can also intuitively know this if you understand that quadrupling the sample size will reduce your standard deviation by the square root of 4. So if you had 4 times as many, and 4 times 160 is 640. So those are 2 different ways to get to 640, knowing the old sample size and the effect on standard deviation you want. The number of undergraduates at Johns Hopkins University is approximately 2,000, while the number of Ohio State University is approximately 60,000. At both schools, a simple random sample of about 3% of the undergraduates is taken. Each sample is used to estimate the proportion P of all students at that university who own an iPod. Suppose that, in fact, P is 0.8 at both schools. Which of the following is the best conclusion? So we're looking at the estimates and which one will be closer to the truth. Will it be Ohio State or Johns Hopkins? All right. Well, first of all, let's say the sample size from Johns Hopkins is 2,000 times 0.03 is 60. Ohio State has 60,000 students, so that would be 1,800 students. So Ohio State's sampling distribution will have less variability because it comes from a larger sample size. So just having that 1,800 in there is going to definitely make for lower variability. Both schools have the same value of P. And remember, we don't use population size when we're calculating standard deviation. It has to do with sample size. Number 7. The student newspaper at a large university asks an SRS of 250 undergraduates, do you favor eliminating the carnival from the term and celebration? All in all, 150 of the 250 are in favor, so this is in their sample. Suppose that, unknown to you, truly 55% of all undergraduates favor eliminating the carnival. If you took a very large number of simple random samples of size n equals 250 from this population, the sampling distribution of the sample proportion p hat would be. So first of all, you can kind of ignore this 150 out of 250. That's just one sample. They told you the true p here, right? It's 0.55. So the mean should be the population mean, 0.55. So ignore that 150 out of 250. We also have a formula for calculating standard deviation. So we're going to put in the 0.55 and the 250 in, and we get 0.031, or basically 0.03. Then the question is this, so you can see we've got A has the correct numbers, C has the correct numbers, and E has the correct numbers. By the way, it almost never will be C. We never know if a population is exactly normal. We never do that. We either do skewed or approximately normal, or something like that. We never say exactly. So, but to test the shape, if it's approximately normal, that's a large counts condition. So we go n times p, and we get 137.5. That's greater than 10. And n times 1 minus p. So the expected number of failures is 112.5, which is also greater than 10. So the shape is approximately normal. Number 8. Which of the following statements about the sampling distribution of the sample mean is incorrect? So we'll go through all 3 of these. The sample mean is an unbiased estimator of the population mean. Yes, they're generally unbiased estimators, unless there's a bad sampling method used. So A is fine. They're not talking about sampling methods. They're just saying, are means in general an unbiased estimator? Usually they are, assuming you're sampling well. All right. Part B, the sampling distribution shows how the sample is distributed around the sample mean. Actually, sampling distributions show sample means, not actual samples, so B is incorrect. Standard deviation decreases for large n, so C is correct, which says the standard deviation of the sampling distribution will decrease as the sample size increases, and that's a general rule, period. D, the standard deviation of the sampling distribution measures how far the sample mean typically varies from the population mean. Yes, that's what standard deviations do. They tell you how things vary about the mean, all right? E, the sampling distribution shows how the sample mean is distributed around the population mean. Yes, that's what sampling distributions are. They're made up of sample means. So the only one that is incorrect is B. Number 9. A newborn baby has extremely low birth weight, ELBW, if it weighs less than 1,000 grams. A study of the health of such children in later years examined a random sample of 219 children. Their mean weight at birth was 810 grams. Now notice that is a sample weight, just one sample. It's not the mean for the population. The sample mean is an unbiased estimator of the mean weight mu in the population of ELBW babies, which means that. So we're looking at the words unbiased estimator. A says the person measuring the children's weights does so without any error. Well, first of all, there's always some variability that has nothing to do with how good the person is who measures. It has more to do with taking a sample, and that's called sampling error, which, by the way, has nothing to do with unbiased estimator. So A is not your answer. All right. So what does being an unbiased estimator mean? It means that X bar for the entire distribution should be relatively close to mu, the population mean. So B says that individual results will be close to mu, but that's not what we're saying. It says in all possible samples, the mean of the means will be close to mu. So C is correct. Let's go ahead and look at the others. D, they're talking about the individual sample mean. That's not the population, so D is incorrect. Finally, in E, it says the values of X bar will have a distribution that is close to normal. Yes, it will, because it's larger than 30, but we're talking about an unbiased estimator. We're not talking about the shape of the distribution. Unbiased means C, that the mean of all the values of X bar will equal mu, the population mean. So the correct answer is C. Number 10, suppose that you are student aide in the library and agreed to be paid according to the random pay system. Each week, the librarian flips a coin. If the coin comes up heads, your pay for the week is $80. If it comes up tails, your pay for the week is $40. You work for the library for 100 weeks. Suppose we choose an SRS of 2 weeks and calculate your average earnings X bar. The shape of the sampling distribution of X bar will be what? So first of all, if I looked at the population distribution, I can tell you it's bimodal. You're either getting $40 that week or $80. Population is when you have a sample of size 1. All right, so what we're going to do is look at all the possible averages for a sample size of 2 weeks. So we're going to look at the results for 2 coin flips. You got flip 1 and flip 2. So if you get heads and heads, that means you get $80 a piece for each week. Divide by 2, you get 80. Heads then tails means 80 and then 40. Average gives you 60. Tails and heads gives you 60 again, and tails gives you 40. So you can see this is actually a trimodal distribution. It would probably be higher in this middle. Remember, each of these outcomes right here has a probability of 0.25. So it is symmetric, but it's not normal. All right. Finally, number 11, an SRS of size 100 is taken from population A with proportion 0.8 of successes. An independent SRS of size 400 is taken from population B with proportion of 0.5 of successes. The sampling distribution of the difference, A minus B in sample proportions, has what mean and standard deviation? So we know the mean here, all right? You just take the difference in the proportions, 0.8 minus 0.5 is 0.3. Where did I get that? I got that from your math chart. So if you look at sampling distributions, you'll see you just subtract the 2 proportions. It's a little messier for standard deviation, and notice you can have different sample sizes there. So we're going to have 0.8 and 0.2 over 100, 0.5 and 0.5 over 400, add and square root, and we get 0.047. So our answer is 0.3 for the mean proportion and 0.047 for the standard deviation of the differences in the proportions.